One of the reasons calculus is so important is a lot of the world around us, we're interested in the rates of changes of things, such as when prices decrease, when your blood pressure fluctuates, the size of the internet increasing. The mathematics of change are really important. Let's start off with one-dimensional motion. Let's suppose we have an object that's moving in a straight line. Its position is given by the position function s is equal to f of t. We're going to assume all positions are relative to the starting point s equals 0. The displacement, or the change of position of the object between t equals a and t equals a plus delta t, is simply equal to the position going from f of a to f of a plus delta t. If I want to talk about the average velocity would simply be the change in position divided by the change in time, or f of a plus delta t minus f of a divided by a plus delta t minus a. If we take the limit of this as delta t goes to 0, I recognize this as my derivative, specifically my derivative of f evaluated at a, and this is our instantaneous velocity. Let's look at an example. Let's say this is a graph of my position function. S is equal to f of t, and my x-axis, this is the time, and I'm going to say these are the hours after noon. Noon is going to be our reference point. And the y-axis, that's going to be our position, specifically in miles. So if I wanted to talk about the location of a car traveling along this curve during the first 3.5 hours of a trip, I could say the following. Between hours 0 and 1.5, it looks like the car is getting steadily away from my initial position. If I look at what happens between hours 1.5 and 2, it looks like there is no change in distance. That means the car is not moving. Between 2 hours and 3.5 hours, the car is returning in the same direction that it went the first time. It's getting closer and closer to my initial point, and then it goes 30 miles past that initial point. Let's sketch what this would look like. At t equals 0, the car is traveling away from its starting point until it is exactly 50 miles away. At that point, the car is resting. And between t equals 1.5 hours and 2 hours, nothing happens. Then the car returns in the opposite direction and goes past the original starting point by 30 miles. And this occurs until t is equal to 3.5 hours. I could also ask a question such as calculate the average displacement between the hours 2 and 3.5. That displacement, that delta s, would be just equal to f of 3.5 minus f of 2. This would be negative 30, because again I'm going the direction past the starting point. Negative 30 minus 50, or negative 80 miles. If I also wanted to know the average velocity, I would just take that delta s and divide it by the delta t, or negative 80 divided by 1.5. 1.5 is 3.5 minus 3. And that's approximately equal to negative 53.3 miles per hour. I could also ask, when is the instantaneous velocity the greatest heading away from the starting point? That would be when the function has its greatest slope. Looking at my graph, it looks like that occurs between 0.5 and 1 hours. The curve looks almost linear at that point, and it looks like that's around my greatest slope. There's an important distinction between speed and velocity. Velocity includes direction, whereas speed does not. So speed is simply equal to the absolute value of my velocity. So that negative 30 that I got in the previous example, if I was just talking about speed, it would just be positive 30. The next thing we need to talk about is acceleration. Acceleration is how fast our velocity is changing. The acceleration is the change in velocity per time. Velocity is simply the change of position per time, so the acceleration can be written as this. The second derivative of the position function with respect to the change in t squared. And here's a nice summary of the acceleration, velocity, and speed. Let's do an example using these three formulas. Let's say I have a cart, and the position of the cart moving along a horizontal track in feet is given by the equation s is equal to t squared minus 5, let's stick an extra t in there, where t is in seconds and t goes between 0 and 5. If I talk about positions to the right of S0, those are positive. Let's answer the following three questions about this situation. Let's first of all graph the velocity function, including when the object is moving to the left, it's moving to the right, and when it's stationary. I want to then graph the acceleration on the same interval, and then overall describe the cart's motion. Let's start with part A. If I've given that the position function is t squared minus 5t, the velocity function, that's the derivative, the first derivative of the position function, then that's equal to 2t minus 5. Let's go ahead and graph that. In fact, what I want to do is I want to do a graph of both s of t and v of t. So looking at the interval from t goes to 0 to 5, we see the position function s of t in red. Looking at the interval from 0 to 5, we see the position function in red. That's t squared minus 5t. We also see the velocity function, v of t, equaling 2t minus 5. If we look at the graph, it's easy to see where the velocity is equal to 0. That looks right around 2.5, and that corresponds to the point in the position where the position function starts changing direction. If I wanted to do this algebraically, I would simply set 2t minus 5 equal to 0. And I would find that at the time t equals 5 halves, which is, by the way, 2.5, the velocity is in fact equal to 0. Prior to that, my velocity is negative, and negative velocity means it's moving to the left. And when t is greater than 5 halves, the velocity is positive, therefore the object is moving to the right, that is, in the positive direction. Now let's look at the acceleration. Looking at the velocity function, it is increasing at a steady rate. So my guess is the acceleration, that will actually be a constant, specifically a positive constant. Let's see if the calculus agrees. The acceleration is just equal to the first derivative of the velocity, which in this case is simply equal to 2. If I add that to my graph, I see that as I expected, the acceleration is just a constant, and it's a positive constant. That is, the velocity is increasing at a constant positive rate. And finally, part C asks me to describe the motion of the object. The cart moves in the negative direction, that is the left direction, until t is equal to 2.5. Then it starts moving in the positive or the right direction, and throughout this interval, it moves with constant acceleration. Let's do another example. This is an example of free fall. Let's throw a rock into a stream from a bridge. The position of the rock is given by the equation s of t is equal to negative 16t squared plus 64t plus 96, where s of t is feet above the water. We want to find the velocity and acceleration functions, we want to know the maximum height of the rock, and we want to know when the rock hits the water. Well, let's start off with the velocity and acceleration functions. If the velocity is the first derivative of the position, then I get this for the velocity function. The acceleration function is simply equal to the first derivative of the velocity, and that equals negative 32. What's the maximum height of the rock? So that means I need to set v of t equal to 0, and I see that algebraically solves for when t is equal to 2, which is exactly what I saw on my graph. The question, however, asks how high does the rock go, not when does the rock hit its maximum height, so I need to plug into my position function the number 2. And when I do this, I get the number 160 feet. When does the rock hit the water? That is on the graph where the s is equal to 0. That is, the position is equal to 0. So let's go ahead and do that. We're now going to try to find s of t such that when its function equals 0. To do this, I'm going to have to use the quadratic formula. And when I solve the quadratic formula, I'll get two separate answers. I'll get that t is equal to about negative 1.16 seconds and t is equal to 5.16 seconds. I'm going to throw the negative time out because that is not in the domain of this problem. I don't talk about negative time. So at 5.16 seconds, the rock hits the water. If I wanted to know an additional question, that is, what velocity does the rock have when it hits the water, the first thing you'd have to do is exactly what I just did. Use the position function to find out when that happens, and then we're going to plug that time into our velocity function, and we get approximately negative 101.12 feet per second. Let's leave one-dimensional motion behind, and let's talk about something called growth models. This is important when it comes to making predictions for things such as growth of population, growth of prices, growth of the size of computer networks needed, etc. Let's say I have, in general, this P is equal to F of T, whereas I'm looking at the population. It could be population, it could be consumer price index. It's basically anything I'm looking at the growth of. The rate of change of my P is simply equal to P prime. If instead of the instantaneous rate of change, I was looking at the average rate of change, that's when I leave it as delta P over delta T. Again, the instantaneous rate of change is when we let delta T go to 0. Let's do an example. The number of internet users between 2000 and 2015 is approximately given by the function P of t equals 6t squared plus 98t plus 431.2, where t are years after 2000. Let's ask some general questions. First of all, what is the average rate of change between the years 2005 and 2010? To figure this out, I'm just going to use the delta P divided by delta T. The population change, that's the difference between P of 10 minus P of 5. Remember, these are t years after 2000. My delta T is simply 10 minus 5. When I plug 10 into my P of T, I get 2011.2, and then P of 5 is 1071.2. I'll divide that by 5, and I get an average rate of change of 188 million users per year. I neglected to say that P of t is in millions of users. If I want to find the instantaneous growth in 2011, I need to take the first derivative of that population function, that's 12t plus 98, and then I simply plug in 11. Let's do a quick graph of this. Looking at this graph, we see that the rate of change of my population is positive and it's continuing to increase. If I wanted to know the predicted number of internet users in 2020, all I would do is plug in 20 into my P function, and that would be approximately 4,791 million users, or about 62% of the world's population. So these are some of the real-life problems that calculus is used to help solve. Let's start talking about business and economic uses. We're going to talk about something called a cost function. We usually call that C of x. That's the cost of producing the first x items. The average cost function, that's going to be equal to the cost function divided by the number of items we're making, and that's usually called C bar. The marginal cost function is a little bit different. That's the approximate cost of producing just one more additional item after I've already produced X items. Usually cost functions will look something like this. So you can see that to produce anything, I have a startup cost of 500. So my cost function is that initial startup of 500 plus 0.1 times x, where x is the number of items I'm making. You can also think of that 0.1 as the unit cost. If I wanted to find my C bar, then that's equal to my C divided by x, or 500 divided by x plus 0.1. I could ask you what's the cost of the first 1,000 items, and that would be 600. If I asked you to find the average cost of making the first 1,000 items, that would be simply 600 divided by 1,000, or 0.6 per each item. That marginal cost, the way we think of marginal costs, that would be the cost of one additional item given that I've already made X items. Well, if we look at this and think of letting the limit as delta x goes to 0, this looks a lot like the change in C divided by the change of x, which is simply equal to C prime. So I'm going to go back in my general comments and add that this is equal to the first derivative of my cost function.